Hello everyone. I am Antonio Virdis from University of Pisa. You of course know the Link Tower. And I work with Professor Giovanni Ste and Giovanni Nardini, two of my colleagues, and we are one of the developers of SimuLTE. And of course it has been quite a long day, so we will try to make this tutorial in a way that the less people as possible will pass out at least. So just we try. And we will talk about optimization in the loop, and just in order to make this thing, at least try this thing make it being interesting for a broader audience, I will talk not so much about LTE and SimuLTE in particular, but we will try to build an example and to understand what do I mean with optimization in this case, what do I mean with putting that in the loop. Okay. We will. This is the quick outline. We will try to build, as I said, an example. So we will do that step by step. So if you have any question during the presentation, just raise your hand. There will be no problem. We will start with taking a look at why do we need optimization with simulation and how we can do that with within the loop of simulation. And we will see two main methods to do that. And then we will conclude with an great example with SimuLTE, so with quite not with a complex module that's SimuLTE. So, as I said, we will start. We will not be technology specific, so we will start with an everyday problem that we can find. So every problem that we find in our work starts with the system, or at least with the model of a system. A very simple one might be composed of a central node that receives packets from somewhere and has to send those packets towards other nodes. Okay, so as every system we find, it has a problem, and we need to solve that. Normally our work is to find some kind of algorithm that can solve the problem. In this case, this central node will probably have to select which are the destination nodes, which priority to give to every single node. So we build our solution, generally an algorithm, and we start our process of debugging and of checking whether it works. Then at some point we have our strong solution. We believe in that. We have any way to demonstrate to the community, to the research community, or to our boss, for example, that our solution wins. So we have to compare this with another algorithm, another solution that's available in literature. Okay, we have to do this because we need to check whether our solution is working, is really working with respect to some realistic results, at least realistic. And we have to demonstrate that I'm better, we are better, okay? In this case, what we do normally is selecting some kind of important KPI in our model and start checking the performance of our system, of our solution against the other. Of course, in this case, in all these cases, we are selecting who is our adversary. So in some way we can kind of cheat, because we will select the system, the configuration of the system, so which parameters are involved and stuff like that. But if we really want to demonstrate that our system is working, it's very, very good, we need to fight against someone that is strong. We have to fight against the optimum solution. Okay. Why do we need to do this? Because once we define the maximum possible solution, we do not have to tell we are better than all the others, but we can say something like we are very, very close to the best possible result. Okay, and of course it's harder to cheat in this case. Okay, apparently it's harder to cheat. Boy. Okay, so We are in this kind of situation. We have our solution that is, as we said, is very strong. Actually, we cannot say that. It's kind of a stupid thing, because we can at least be very close to the optimum, but we cannot, of course, be better. Otherwise, we will be the optimum. Anyway, once we are in this situation, we have to check the difference between those elements. But the first thing is understanding what is this. Normally, the optimum results, it comes from mathematical formulation of our problem. For example, as a definition of an optimization problem, like in this case. So we are basically defining an objective function that tells just maximize this kind of variables of the system, subjected that we have a certain number of constraints. Okay, so we can model our system this way, and we can see what are the best results we can achieve. A normal question that arises is, why not using Superman in this case? It's the strongest, why not? Because generally, when we define a mathematical problem, first thing, we will not be able to solve that in a reasonable amount of time, of course, because we want to use this with our system. So if this is a very complex optimization problem, it will need a lot of time, possibly a lot of time to be solved. Moreover, sometimes those problems are not cannot be solved in the original form, because they cannot be solved by commercial solver, for example. So they need to we need to make some kind of simplification to them. So it will be not completely close to reality. So we have to, at least we can use this, but we can of course maintain our original solution. So we will start building our example, and we will start from again a generic system. We see this is the first element we saw before, and for example is an element, a network element that is receiving packets. Those packets will come into buffers that will be filled, okay? And then we have a finite number of resources, generic type of resources. This can help just imagine your own problem, and then we'll probably have some kind of similarity with this. And then those buffers will be the output buffer towards other nodes, okay? And of course, we have the problem to solve. In this case, we are generally dealing with the scheduler, because we are dealing with the kind of scheduling algorithms, because we have to decide which, given the finite amount of resources that we have, which will be the actual target of our communication, okay? In order to optimize some kind of KPI. But once we have this system, how can we actually obtain the results we saw before? So use that with Superman, with our best results. One possible technique is using our system as it is, and then taking what we call snapshots, photographs of the status of the system as it is going into the scheduler, so into the problem that has to be solved. Once we have those, we can feed that to our mathematical formulation, to our optimization problem in this case, that is our best algorithm. And afterwards we can take the outputs from both the original solution, our solution, or the other, possibly the second algorithm we saw before, and compare that against the optimal solution we are just obtaining. Okay? So this is a possible solution that I think it's widely used in many papers around, many research projects. But in order to understand if we are understanding something, we try with a very simple quiz. Just imagine the system, the problem that we are trying to solve now. Okay, so we have a scheduling problem with two buffers that are receiving packets, a finite amount of resources, and a timeline that's quantized. So we will do operation every t. And we define for each of those q an output speed. Okay, so given the same amount of resources, in this case, speed 1 of the first queue will be higher than speed 2. So given the same amount of input packets that will be received, and if we send those out, we will obtain better performances. Okay. For example, if okay, no, just take this. And we have as input an infinite number of packets. Okay, that are coming and will fill the buffer. So we are in a situation that is often called full buffer. Okay. So if you have to just think of, you have to build the perfect algorithm in this case, or at least the strong algorithm that we are trying to build in this case, what will you do for each time instant here? Just think about that. I know it's a very simple problem. Normally, for each step, the algorithm will take a look at the two queues, in particular at the speed of those two queues, and it will select the fastest one, of course, because it's a little bit trivial. Then, for the next step, the resources will be freed. We will take a look again at the speed of the two queues. We will see that both of them are full, and we will select again this queue. Okay. As we go forward, of course, what we obtain is a known phenomenon of starvation. So we are just selecting always the same queue. So because our KPI in this case of obtaining the most amount of resources and on the output. But what will happen if we are in a case like this? We have as input a finite buffer, for example, a CBR, constant bitrate input. Okay. In the same case, if we apply exactly the same algorithm, we will probably obtain something like this. T0, we apply the same algorithm, we select this queue, allocate all the resources, and okay. First step. What will happen after we process this? Exactly this. Because we have a finite number of packets incoming, we are changing the status of the system. Quite simple. So in the next step, we will select the best speed. We will send all the packets that are in queue, and then we will end up using the other packets. Okay? The same thing. And the system will evolve this way. What is happening here with respect to the previous case? What is happening is that the status, the state of the system, depends on the decision that our algorithm is making and is taking. Okay? So actually, what is happening as T1 depends on T0. And this is true on the general case. So when we are considering our model here, we have to consider not only the inputs of our scheduling problem here, but also the decision. So we are starting to create what I was calling at the beginning the loop, the simulation loop. Okay? So the behavior, and in particular the effects of the scheduler depends on what has happened in previous time frames. And in our case, the effect of the decision is the change of buffers. But we have to apply this not only in this case, but also in this one. Okay, this is the real difference is here. Because if we just use, as we saw, the fact that we were using the scheduler in, we'll take a look at, looking at the scheduler in the case of without the loop involved, we were obtaining a performance that were surely better. That's the second case, because we were always selecting the best, only the best. Okay. I'm not saying that this is correct and this other is not. They are just different. Probably that one is an upper bound to performance, and that one is something probably that is probably in the middle. The important thing here is that we keep two status of the system separated. Okay, so as to that the evolution. The evolution of the two systems will be independent. Moreover, another important thing probably is to keep the random number generation independent. Of course, if we have two separated systems, we are obtaining this. But what will happen if the random number that I'm generating do depend on the scheduling decision? For example, because I'm generating a packet every time I send some packet out. Of course, those two streams will diverge as the simulation progresses. Probably in this case, it's just a good practice to separate, to use different streams. One for the things that are depending on the scheduler that we are using, another for all the other stuff. For example, one for scheduled packet generation and one for mobility, generating errors in the channel and stuff like that. Okay. So once we have defined this problem, we have to actually going into the loop of the simulation and taking a look at an actual simulator. So of course we will consider OMNeT++ for the purpose, and we will use as a solver for solving our optimization problem SimuLTE. I was telling before that actually I realized today that I'm proposing something that from this building itself, but of course I knew that SimuLTE was made by IBM, but anyway, it was not made on purpose. So actually the reason why we are using SimuLTE is that is widely used by the research community, even for commercial purposes. And it's quite flexible. It can be used to solve linear programming problems, and in some cases even non-linear programming problems if those are convex. Program problems with binary values, integer values, real numbers and stuff like that. And last but not least, it has a research kind of university program, so it can be used free of charge by researchers that are adhering to that program. Okay, so we can actually use in our case. So what do we need to do? First of all, we need to realize a model of our system within OMNeT. And I have no doubt that everyone here knows how to do that, or at least knows how to ask to do the same thing. So the first thing is building our model. Then we have to figure out and to isolate where the actual problem is. Why do we need to do that? Because we need to create an interface between the actual problem, the actual system, and the solver. Okay? And if we are able to isolate this, we can just use this as an interface. Okay? It will be quite simple to perform all the other stuff. The first step we need to do is reading the system information from the system status itself, all the relevant system information that are needed by the scheduler, and we need to build a program instance. Okay, you know, mathematical problems are abstract, so we have to create a real instance using the status of the system to create the actual problem. We have to solve that, here, and obtain the results in our interface. And last, we have to parse the solution, the results, and enforce it within our system. We can see we have two main parts. The first one is step 1 and 4, and is responsible of, is dependent on the system that we are simulating, okay? And the second one is steps 2 and 3, and is dependent on the solver that we are using. If we are able to separate this part this way, we just need to change step 1 and 4 if we change our system in this part, and we are just to change steps 2 and 3 if we change solver. Okay. We will focus on these two parts that are common to most of the problems, and I'm going to propose you to suggest you two possible methods. The first one plans at using the simulator, so OMNeT, and the optimization program as two separated entities. Okay, and we will use SimuLTE as an external program. So using something that's called interactive solver, and can be used via command line. Okay, so it's an independent program. What we need to do is create, performing a communication using files, for example. So we need to create a linear programming file and feed that to the solver. And we need to create an XML file that will be created by the SimuLTE system, and we need to be able to parse it, and so to enforce the decision. The second solution is merging the two parts into the same simulation environment, and we will see this second part. Okay, so starting with the first method, we take a look at building the problem. So we have the generic representation of a mathematical problem, and basically what we have is a lot of mathematical symbols, something like summations, and for each here symbol. And what we need to do is basically expand those symbols. If we start, for example, with the maximization part, we may create a lot of for loops, okay, that are at the size of the extremes of the summation, and we just have to write all those parts, x0, x1, x2, and stuff like that, into a stream. For example, a file stream. Okay. Similar thing we can do for each part, for all the constraints, and we this way can create a representation of the optimization problem that's very similar to this one, but just bigger. To obtain a big file. Once we have this is a format of the file that can be used with OMNeT, with SimuLTE. So we just have to use a system call, for example, the system call, and call the interactive solver using a string of parameters. Okay. This way we are just calling the external program. The simulation will just stop because we have called a blocking function, a blocking system code, and we'll wait until the optimization is complete. Okay. So in this case, we have no problem of synchronization. That was something that we were discussing before, because the simulation is just the simulated time will be suspended and will restart exactly in the same moment, unless we decide to shift that using some kind of model of the computational time. Okay. So once we have we created our file, we solved the problem, and we will obtain results in terms of an XML file. So what do we need to do at this point is just being able of do XML parsing. We can either do this using built-in OMNeT functionalities. I just tried this once. I think I also talked with Rudolf sometimes. I was not directly able to do that, but I think that is possible using something like that. Otherwise, just in XML file, so it's easy to parse that manually. So we can just find the part we are interested in and read that. The format is a long XML file. At the end, we have a part with the variable fields. And we can either read those by the name of the variables or their indexes. Okay, so it's very simple doing this. And of course, we read the values and we can enforce that in our system. And then here arises a very simple question: but can we do something like this with an API? Actually, yes. Cplex offers two kinds of APIs. The first one is called Callable Library. It's a matrix-based, I will explain what I mean with this, C-written API. And the second one is called Concert Technology. It's a set of modeling objects that has been written also in C++. We have selected the Callable library because of several reasons. First of all, it can be used in a way that's very similar to the previous case. So we can build a problem in a similar manner to what we see in the first method. Second, the concert technologies we need to rethink of our way of building the problem. So it was not immediate, but can also be done. We can do the same thing with the concert technology. So the first step is the trickiest, as convincing OMNeT to use Cplex as an API. Okay. At first it was very tricky, but afterwards not that much. Once you of course find someone that has done that. The first thing we need to do is tell OMNeT where the either files are located. Then where the dynamic libraries that are used by Cplex are located again. So for example, dynamic libraries for creating the threads and stuff like that. Then we have to tell which libraries has to be included and enable some preprocessor macros. This can all be done using the project properties. Okay, I'm not going into detail on how to do that, but if you need, I can share a very nice README with you. So everything can be done quite easily. How does this Callable library work? I said that we have a matrix representation, where we can describe, for example, the objective function. The objective function was the upper part we saw before, so maximize something. We can represent that using a vector, an array in C. And we can associate each element of the vectors with the variables that we are using. Actually, this vector will contain all the variables in the system, not only the ones that are used for the objective function. Okay, so simply what we need to do is just setting to 0 the coefficients of those variables that will not appear in the objective function, and these will be the coefficients of all the other variables. The system actually just takes a look at the variables this way by their index, so it's quite an abstract thing. And of course we have to create the constraints, and here the things start to be a little more complex, because for each constraint, for example, x0 plus x1 is less than something, we have to create another vector. And for each element of this vector, we will have to tell which are the variables that are involved. And we have to do this for all the possible constraints that we are considering. And moreover, we have to tell where each constraint actually begins. Okay. So those are all arrays, C arrays. Okay. As you can imagine, what will happen if we have quite a big problem? We have a very long set of variables, a very long set of constraints, and we'll find something like this. It will start to be quite complex and especially very error prone to find a solution, to find a way to manage this. Okay. So one way to possibly solve this is using, we propose a custom, very simple custom C++ interface that can actually be used to solve this problem and to automatize some of these parts. First of all, we have to notice that all the variables are in this form. xi, for example, we have one predix, or for example with two predices. Okay. So once we notice that, we can just also notice that if we have the first predix that goes in this range and the second one in this other range, we have a variable that will have this kind of size. Why is this important? Because we can use this size to define its position in the array. It's quite simple, but the idea is making this kind of an automated process. So we can represent each set of variables with three fields. Its name, for example, in this case x, and the amount of the range of their predices. So for example, xe as the first predices that goes from 0 to m, and has no second predis. Then the same thing with y, and for example, if we have a different one, we can represent all these elements this way. What we obtain is that we can access all those variables with their local indexes, okay, and we can use that in a way like this. So we can access all the elements here. Similar thing we can do with the constraints. We can create the constraints all one by one, just using the local indexes, and build the problem at the end with just one shot. Okay, so we are just automatizing all the process all together at the end. The last step is just reading the output. Given the fact that the XML was made this way, we can just use the same method here. So we will have a solution vector, a solution array that we will define with the indexes of the variables, and we can either use local indexes or global indexes, as we saw before. And here it comes the second quiz. Just suppose we have an optimization problem that's composed only of binary values. Okay, so every variable can assume only 0 or 1. Okay, we obtain our result vector. We can access it in this way, like a normal array. If we have to perform the last step, so reading the results before seeing the solution, can we just do something like this? So can we just compare the values of the variables this way? In the first version of the solution, I tried something like this, and I obtained a program that was, of course, not functioning, and I started the long debugging process. And I printed out all the values and obtained something like this. That was okay from my point of view. But I was still not understanding why this was not working. So I increased the precision of the cout that I was using for printing out the elements, and I discovered something like that. And then I took a closer look, and I find this guy here. So when I was reading all the binary values within the system, I remember something that is, do not trust double values when every time you are dealing with them, because the result that we are, the result vector that we are using is a vector of doubles, and it's not important that it has to deal only with 0 and 1, depending on the representation. At 1 somewhere it may happen. So with a simple round operation, we can solve this. We have these two solutions, and we can analyze pros and cons of them. The first one, based on generation of files, is very easy to build, okay, because we have just to write files, but it's generally slower because we are calling from OMNeT an external program. So every time we use the system call, we are changing the context of the program. So you have to pay the time for that. Moreover, we are generating files, so we have to work on disk. We can, of course, eliminate this problem if we use memory mapped files, but it remains an issue anyway. The second method is generally faster because it is built in within the system, but requires the knowledge of the API that we saw before. It can be solved with a custom interface, but it still remains a problem. Okay, so we have our system model, and as I said, we can try this with a realistic example. So we will try to use that with LTE and SimuLTE. SimuLTE is an INET-based model for LTE network, and as I said at the beginning, I will not go into detail of LTE. What we will just try to move for this original example that we can understand and use that for LTE as well. And we will carry with us our best solution. So basically, what is LTE? LTE is a cellular network that's composed of a main base station, that's the main antenna that is sending information and receiving information to user equipment, so to cell phones. And it's doing this on a 1 millisecond basis. It has a certain number of resources that are called RBs, resource blocks, that can be used by the eNode B to serve the users. Of course, the eNode B has a set of buffers that can be used to store data coming from other networks, for example, from the internet, to send them towards the user equipment. Moreover, we can define something that's called the channel quality indicator. It's basically the speed that we saw before for the output queues. So it's just a way for each user equipment to tell, given my channel, I can fit 90 bytes, I can receive messages with 90 bytes on each resource block. So it's the same thing as the speed we saw before. In this case, user equipment 1 will have an higher CQI with respect to user equipment 2, okay? Because 1 can fit this amount. So the same problem as before, we have to create a scheduling algorithm that will divide and the resources among the elements. So the resource allocation problem is the same as we saw before. We have buffers, packets that are incoming, a finite number of resources, CQIs that are the speed, the output speed of all those elements, and basically we have to allocate RBs among the user equipment. The same problem as we saw before. Actually, this is a little more complex, something like this. So the problem can be seen as a problem of multi-band scheduling, because every resource block is different. So every user equipment, every cell phone can experience different channel condition, and so have a different speed on every resource block. But we have to select only one of these. So this is a problem that's known to be NP hard, and in certain conditions can be solved with optimization solvers. Okay, so this is a typical case of comparison between a best solution that is feasible only in certain case, and so we have to create a heuristic for this. Okay, we are going to see how we can implement such kind of scheduling solution within SimuLTE. So SimuLTE is actually focused on solving resource scheduling algorithms. It's composed, the node B, the main node that's in node B, is composed of course, of a lot of system layers. And in particular, we have a layer that will deal with the resource allocation. So on how those resources are allocated, how many of them are available, something like that. We have a module among all those compound modules here, a simple module here that's called allocator that is responsible of asking resources with respect to the resource status of the system. And we have a separate set of scheduling modules that are responsible for deciding how many resources to allocate to each user. So, okay, we have different connections between all of those modules. Why we are doing this? If we take a deeper look of the hierarchy of the elements, we have those two interfaces here that are responsible, again, as I said, to check how many resources are available, and another connection to see how many users are alive, how many data are coming from the network, and stuff like that. And we have to implement our actual scheduling policy, so our actual algorithm. In order to keep this separate, as we said at the beginning, we implement the scheduling policy as a base class that can be extended into several algorithms by just extending the base class and implementing separated function. And of course, we can do the same thing with our optimal solution. As I said, we are doing this because we need, again, to separate the steps of obtaining the status of the system and enforcing our decision with respect to the communication to the solver. Okay, so again, we can change here the solver that we are using, the same as we can change the system, of course. Okay. So once we are in the situation, we can try to look at a real example. I tried with with a scenario with one node B that receives traffic from CBR sources and has a certain set of user equipment that's configurable that are receiving data from the CBR source. Okay, and all here in the middle there's the SimuLTE model. We configured that with, I think, in this case, 10 users, and we tried that with varying packet sizes. So in order to take a look at how the system was varying, the system load was varying. For example, with linear mobility from OMNeT, and with the objective with the goal of taking a look at the difference between in-loop optimization and out-of-the-loop optimization. What we obtained was something like this. We have the throughput as seen from the MAC layer, so the amount of bytes for each for each milliseconds of the system time for various packet sizes, okay, expressed in byte. In blue we have the heuristic algorithm, a simple heuristic algorithm that can be used in this case, and in red we have an optimization problem that is solved within the loop of the simulation. As we can see, the main differences, we can see that we have a lot of improvement in performance for high loads. For lower loads, we have kind of similar results. Okay, of course, because the network is quite empty here. But what happens if we consider the first example we saw at the beginning, so the optimization out of the loop? We obtain this result. Okay? So actually, using the same mathematical formulation, exactly the same, we are obtaining a totally different behavior. In particular, in this case where we have the expected similar behavior in performance between the heuristic algorithm and the optimized one, we are obtaining not similar result but very different. On the contrary, here, for the maximum occupancy in the network, we are obtaining the same results between the out of the loop optimization and the in loop optimization. The reason we are obtaining this is just given by the result of quiz 1 we saw before. Because in this case, the heuristic algorithm is just able to obtain very close, it's just able to empty the buffer in a very fast manner, but not as fast as the optimization solution. So what will happen is that this green part will see buffers that are on average with more packets. Okay, so it is basically cheating. Okay, so as the system load increases, what we will obtain is that the status as seen from the loop, the optimization in the loop and out of the loop, will collapse, will be very similar, because no matter what we do, all the buffers will be full. Okay, so this is the main difference. As I said at the beginning, whether using simulation in the loop or out of the loop, there is no right or wrong choice. Those are simply different, and we can use those within our simulation models and without our research that use simulation to discover just the strange behavior of our algorithms. Okay, so I think we end up a little earlier. So if you have any question before running for dinner, I'm available.
We're coming about 5 minutes. I do have a question. I maybe touched upon it briefly, but actually Bogdan did actually all of that work. We did quite some effort in applying linear programming to specific problems that were actually OMNeT related, but it was not in the loop. Basically, what we're trying to do is kind of find optimized routings for specific traffic patterns to minimize the number of conflicts. And having gone through that experience, I would be kind of skeptical of trying to put that in the loop, because these linear programs, they explode very quickly in terms of just the file sizes, right? And then actually having to run the solver on that. We found that even for very small problems, unless you think very hard on how to optimize the formulation of the linear program, it's off scale.
Yeah.
So what's your experience with scaling this?
Yeah, my experience, that is exactly what I was trying to explain at the beginning. We cannot use Superman because of what you are just saying, right, because it will not scale. In fact, actually, the example I was showing you is made with a very, very small network. So I just told you that we were only one antenna and 10 cell phones. So it's kind of the desert. Okay, but it was just useful for testing purposes. I agree with you. You cannot do a large-scale simulation with this. The good thing is that if you are using in both methods, both the first one and the second one with the API, you are using the Cplex environment, so the environment of the optimization tool. So you can use multi-core. So if you just need to increase a little bit, I said well, a little bit because those problems scale like this. A little bit of more complexity in the network configuration, you can try at least to increase the number of core that you have without changing at all the model, the implementation, whether it is in OMNeT or in other cases, for example.
Okay.
Again, but it can be used especially for testing purposes and to fill the related work by part of the papers. You know that you have to write something there.
Any other questions?
No, I'm just sure.
Just for me to know, like, what is SimuLTE? What is it? It's a sort of a simplex equivalent, or
SimuLTE?
yeah?
No, SimuLTE is the model of LTE
In OMNeT.
in OMNeT. It's an iNet based OMNeT.
I didn't know that. That's why.
Okay. I'm just interested in whether there are people that are using optimization in some kind of the research work, and if they are thinking about using it in a way like this, because I see that in a lot of papers, but actually I never found someone that actually used that in programming. Okay.
I think they're using it to some extent, but out of the loop definitely.
Yeah. Okay. I think this is an answer. Okay.
Okay, then let's thank Antonio once more. So that finally brings us to the end of the technical program for today. So I thank you all for your patience. You've been very brave.